All right, hello, we're back here to finish task 3.9. Let's get straight into it. From the last we left off was on number 10. The thing says, look back at the work you did in the task to be determined. Which quadratics in that task had complex roots? List them here. So we're going to go back to be determined, which was task 3.8. We're going to look to see which had complex roots. So we're going to look to see which ones had complex roots. And it turns out it's actually this one. Right? This is the one with complex roots. Remember, complex means that it has an imaginary component. In this case, we have here the square root of -1, which we now know is called I. So this is -2 plus or minus I. And that makes these solutions complex roots. So it says list them here. X squared plus 4x plus 5 is the answer. Let's keep looking. This is also one, and that was x squared plus 4x plus 6. Okay, and those were the two that had complex roots, yeah. So the question says, how can you determine if a quadratic has complex roots from its graph? Well, if the graph does not intersect the x-axis, it has complex roots. If the graph does not intersect the x-axis, it has complex roots. Okay, this one says, find the complex roots of the following quadratic function represented by its graph. So we need to find the complex roots of this function. We can see here the vertex is -2, 3. So we can start to write a vertex form. X plus 2 squared plus 3. We can see that it is following the parent function, so there's no dilation. So what we want to know is, where does it equal 0? Now, it doesn't equal 0 anywhere. At least the graph doesn't cross the x-axis, but we can still solve it. We can subtract 3 from both sides. Take the square root of both sides. This will be plus or minus. The square root of -3, we can separate that into the square root of -1 times the square root of 3. And that will equal I root 3 like this. We can subtract 2 from both sides. And these are the two roots, -2 plus I root 3 and -2 minus I root 3. Okay, and then it says, let's see, reflect the graph of the quadratic function given in question 12 over the horizontal line y equals 3. Find the irrational roots of the reflected quadratic function. So the line y equals 3 is right here. And it says to reflect it. That means this point is not going to reflect anywhere, but this one will reflect here. This one will reflect to here. We'll get a graph here like this. And so we get this here like this. So it's reflected. And then it says to find the irrational roots. Well, this has the same vertex and the same dilation, except it's negative. So let's write the same equation we did before, except that it's negative. So that would be negative x plus 2 squared plus 3. And then we'll solve this when it equals 0. So we can subtract 3 from both sides. Now we can divide the negative sign from both sides. We can take the square root of both sides. And that's going to give us the square root of 3 plus or minus equals x plus 2. And we can subtract 2 from both sides. So these are the solutions for when it was reflected. How is the work you did to find the roots of the quadratic functions in question 12 and 13 similar? Well, the solutions are actually, if you look, they're actually almost the same. This is -2 plus or minus I root 3. And this is -2 plus or minus root 3. So the only difference is that this one doesn't have an I and that one does, because this one doesn't cross, or excuse me, this one does cross the x-axis and that other one did not. So the work is almost identical. Except we could cancel the negative sign this time. Okay. Complex, so big idea number 3, complex numbers are not real numbers. Okay, they lowercase real numbers. Okay, remember real is a type of a category of number. Obviously, complex numbers are real in the fact that they, they're actual numbers, but they're not, the values that they represent are not categorized as real values, if that makes sense. So real in this sense doesn't mean real like how people normally mean it to mean. It means real in the sense of the category of real numbers, like the name. Okay, that means they do not lie on the real number line that includes all of the rational and irrational numbers. Also note that the real numbers, these should all be capitalized. The real numbers are a subset of the complex numbers, since a real number results when the imaginary part of a plus bi is 0, and that is a plus 0i. So what that means is, if you drew a Venn diagram, right? So normally Venn diagrams are like this, where there's a part that's over here, there's a part that's over here, and there's a part that's kind of shared, right? So the Venn diagram for complex and real is more like this. Here are all the complex numbers, and the real numbers are inside the complex numbers, right? So every real number is also a complex number, but there are some complex numbers that are imaginary and they're not real. So that's what it's trying to say. And what it's trying to explain here is, look, here's a complex number. Well, if b is 0, 0 times I is 0, and so you just get the a part, which is the real part. So anyway, let's keep going. Remember the following information given in the previous task. A polynomial function is a function of this form, where all of the exponents are positive integers and all the coefficients are constants. As the theory of finding roots of polynomial functions evolved, a 17th century mathematician Girard made the following claim, which has come to be known as the fundamental theorem of algebra. An nth degree polynomial function has n roots. We already have heard this before, but this is just refreshing. And then it says, based on your work in this task, do you believe this theorem holds for quadratic functions? Do all functions have 2 roots? And the answer is yes. Right? Yes, they do. They're either 2 real roots or 2 complex roots, or it's 2 roots, but it's the same root, like it's the repeated root. Okay, let's do some ready, set, goes. Okay, classify each of the numbers represented below according to the sets. Remember, the sets means categories to which they belong. If a number fits in more than one set, then list all that apply. Okay, so pi is not a whole number, it's not an integer, and it's not rational, but it is irrational. So we're going to list it with a Q with the line over it. It is a real number, because irrational numbers are all real numbers, and then real numbers, every real number is a complex number as well. So this is also a complex number. 0 is not a whole number. When we think of whole numbers, we think of counting numbers. Usually we think of the natural numbers. Well, whole numbers might actually include 0 as well. We're going to say for the purposes of this assignment that 0 is not a whole number, but it is an integer. So it does belong there. It is rational. It is real. And it is complex. It fits in all those categories. Oh, I should have gone across. Negative 13 is, I'm just going to cross this out because it's possible that whole number, when I think of whole numbers, I think the same as integers. Now, there might be some nuance there, but I do not currently have that nuance. So we're just going to use integers. Negative 13 is an integer. It is rational. It is real. And it is complex. Okay, this square root of negative 16 is not an integer. It's not rational, irrational. It's not even real. It's only complex. And that's because of the negative under the square root sign. The square root of 75, if we reduce that, that's going to be, can we reduce it all the way? Can we simplify it? 25 times 3. This is 5 root 3. Okay, this is not an integer. It's not rational, but it is irrational. It is real, and it is complex. Okay, 9 over 3 is not an, oh, is it an integer? It is actually. 9 over 3 is equal to 3. So this is actually an integer. It is rational. It is real, and it is complex. All these numbers, by the way, they're all complex because complex, for the type of math that we're talking about now, complex numbers are like all the numbers that we have talked about so far. Okay, the square root of 4/9, well, we can take a square root of the top and the bottom. That's going to give us 2/3. This number is not an integer, but it is rational, and it is real, and it is complex. This number is not an integer. It's not rational. It is irrational. It is real, and it's complex. This number, because of the negative under the square root, is only complex. Okay. Let's go to the set. Simplify each radical expression below. Okay. We have 3 plus square root of 2 minus 7 plus 3 root 2. So these two guys here are like terms. That's going to be 4 root 2. And these two are like terms, which is going to be negative 4. So this equals negative 4 plus 4 root 2. Okay. Basically, everything that has a radical combines, as long as the inside part, we call that the argument. As long as the argument, the inside part of the radical is the same, you can combine like terms. But they cannot combine with just these constants here. Okay, let's go to number 11. All of the radicals have the same argument of 5, so we can do this. Square root of 5 is going to go together with 8 root 5. It's going to go together here. These guys actually cancel out because this is positive, that's negative. So all we have left is there, and negative 9 plus 11 is 2. These ones go together. So we have 2 plus 8 root 5. That's our answer there. Okay, let's go here. Okay, these do not have the same argument, and meaning inside they don't have the same. But if we simplify them, they might. So 12 is 4 and 3, so that's going to be 2 root 3. 48 is 16 and 3, so that's 4 root 3. And we can combine these to be 6 root 3. Okay, these ones, okay, 8 is 4 times 2, so that's going to be 2 root 2. 18 is 9 times 2, so that's going to be 3 root 2, and it is being subtracted. And 32 is 16 times 2, which is going to be 4 root 2. So here we have 2 root 2 minus 3 root 2, so that's going to be negative 1 root 2, plus 4 root 2, which is going to be 3 root 2. Okay, these are already kind of like terms. 11 minus 5, 11 root 7 minus 5 root 7s. It's going to be 6 root 7s. You can also think of the roots as kind of like units. So it's like saying 11 inches minus 5 inches, it's 6 inches, right? The radical, it has some similarities. You can think of it like that. So here we have 5 root 3 plus 1 root 3. That's going to be 6 root 3. Negative 3 root 7 and 7 root 7 is going to be 4 root 7. That's it. Okay, simplify, express as a complex number using I if necessary. Square root of 2, negative 2 times the square root of negative 2. Since it's repeated, this is just going to equal negative 2. This is going to be 7 plus 5i. This will be 4 times 4, which is 16. I times I is negative 1, so this will be negative 16. Okay, this is going to be negative 1. This will be I squared. That's going to be negative 1 squared, which will be 1. So that's just 1. This is just 1. And this is going to be I2 times I. So that's negative 1. Negative 1 times negative 1. It's going to be positive 1. So this is really just I. Is there another way to do that? Yeah, we can add up all the exponents. So that's going to be 5, 6, 7, 8, 9. Right? I squared times I to the third times I to the fourth is equal to I to the 9. And that's the same thing as I times I to the 8. And that's the same thing as I squared times 4, or I squared to the 4th power. That's going to be I times negative 1 to the 4th power. Oops. So that's I times 1, which is just I. So that's the solution. Remember, it takes 2 i's to make a negative 1. Okay, square root of negative 4 to the 3rd power. So that's going to be square root of negative 4 squared times square root of negative 4. Square root of negative 4 squared is just, this will just be negative 4. And then this is going to be 2i. So that'll be negative 8i. Okay. Here we have 2i times 5i squared. So this will be 2i. We need to do order of operations here. 2i, 5i times 5i is going to be negative 25. And then that will be negative 50i. Okay. Let's keep going. Solve each quadratic equation over the set of complex numbers. So let's just solve these. So if we subtract 100 here, we get x squared equals negative 100. If we take the square root of both sides, x equals plus or minus the square root of negative 100. The square root of negative 100 is 10i. So x equals plus or minus 10i. Okay, let's go over here. T squared equals negative 24. So t equals plus or minus the square root of negative 24. So we know that's going to have an I. 24 is 4 times 6. So we can pull out the 4. That's going to be t equals plus or minus 2i root 6. Solving this one, we can do a completing the square. We need a 9. X squared minus 6x plus 9. plus 4 equals 0. Okay, and then this gives us x minus 3 squared plus 4 equals 0. Subtract 4 from both sides. X minus 3 squared equals negative 4. X minus 3 equals plus or minus the square root of negative 4. This will be 2i. So x minus 3 equals plus or minus 2i, and then we add 3 to both sides. X equals 3 plus or minus 2i. Okay, over here we get r squared minus 2r plus 1 plus 4 equals 0. This is going to give me r minus 1 squared plus 4 equals 0. R minus 1 squared equals negative 4. R minus 1 equals plus or minus 2i. That's taking the square root of both sides, adding 1 to both sides. R equals 1 plus or minus 2i. Okay. Use the discriminant to determine the nature of the roots to the quadratic equation. Okay. So the discriminant is the part of the quadratic formula that's under the radical. So the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac over 2a. This part here, b squared minus 4ac, if it's positive, you have two real solutions. If it's negative, you have two complex solutions. And if it's 0, you have a repeated solution. So let's see. 5 squared minus 4 times a times c. So 25 minus 4 times 7 is 28. It's going to be negative 3. So these are complex solutions. Okay, that's going to be 25 minus 4 times 1 times 6, which is 24. That's going to equal 1. This is real solutions, two real solutions. Okay, here we've got 25 minus 4 times 2, which is 8, times 5 is 40. It's going to be negative 15. These are going to be complex because it's negative. I'm basically just plugging it into here to see if this would be negative, because if it's negative, then we take the square root of a negative number, and that would lead to a complex answer. So here we have 49 minus 4 times 1 times 2. That's 41. This is going to be a real solutions. This is 49 minus 4 times 2 is 8 times 6 is 48 equals 1. So these are still real. Here we have 49 minus 4 times 2 is 8 minus 56. These are complex. This is 49 minus 48. This is real. These look the same. The only difference is the negative 7, but since we're working with b squared, it doesn't matter. These kind of look similar too, but the negative is over here. So we've got 49 minus negative 48. That'll be positive. Double negative means it's going to be positive, so this will be real. Here we have 3 plus, no, that's a lie. We have 36 plus or minus, no, that's no, there's no plus or minus. 36 minus 4 times 1 times 9 minus 36. This is 0. So this is going to be a repeated root. Or it's a repeated real root. That's the only one that was repeated because it equaled 0. Solve the quadratic equations below using an appropriate method. Okay. Can I factor? I immediately go to factoring. Factoring is like, can I factor? If yes, do it. If not, find something else. So can I factor this? Yes. 56 is 8 times 7, and 8 plus 7 is 15. So this would be m plus 8, m plus 7. So m equals negative 8, or m equals negative 7. Done. Okay, can I factor this? two numbers that multiply to 35 and add up to -3. Well, 35 is 7 times 5, and that's it. So the answer is no. So we're gonna plug this into the quadratic formula, because the reason why is because I don't want to deal with the fractions of having to divide everything by 5. So we're going to plug this into the quadratic formula. So that's -b, and that's -3, double negative. So 3 plus or minus the square root of b squared, 9, minus 4 times a times c. 4 times 5 is 20, times c is 140. Over 2 times a, which is 10. Yeah, see, it was going to give me a complex number anyway. I wouldn't have been able to factor this. 3 plus or minus the square root of -131 over 10. So we can say 3 over 10 plus or minus I square root 131 over 10. Okay, can I factor this one? 21 is 7 times 3. Yeah, I can factor this. We can do x minus 7 and x minus 3. So x can equal 7 or x can equal 3. Okay, and can I factor this? Two numbers that multiply to 30 but adds up to, or to -30 and adds up to 7. Yes. 6x squared plus 10x minus 3x minus 5. Factor out of here, factor out of there. I can factor 2x here. 3x plus 5. And I can factor -1 here. 3x plus 5. That gives me 2x minus 1 and 3x plus 5. So x can either be negative, or x can be a half, or x can be -5/3. That is the end of task 3.9. All right, everybody, next time you'll see task 3.10, I numbers.